Hello and welcome to the third and final module of lecture 2. So in this module we shall discuss two topics. One is so far we have seen circuits with no mutual inductance. Okay, so we consider these inductances to have no coupling between themselves, right? And we saw that life was pretty easy. We could just take a quick look at the circuit, and we could easily write out these KVL equations, right? They're quite straightforward. Things become a bit complicated when you have mutual inductances and you have to follow something called the dot convention. So we shall briefly touch upon this dot convention and what is at the heart of this. And once we are done with that, then we shall look at something called operational amplifiers. So these are basically active elements. So far you've seen resistances, inductances, capacitances. These are all passive elements, right? Then we'll see now operational amplifiers, which being active elements, that means they have their independent voltage sources, energy sources. And these operational amplifiers also have certain transfer functions, right? And we shall see how to derive those transfer functions. We shall see what the ideal op-amp assumptions are. And then if we remove those, if we get rid of those assumptions, then what the equivalent circuit of an op-amp looks like. We shall just look at the structure, and hopefully by the end of this module, we shall be able to solve using Kirchhoff's current law, KCL, the transfer functions. We shall be able to obtain the transfer functions for operational amplifiers, even those that are non-ideal. So that is the goal of this, those are the goals of this module covering these two topics. So without further delay, let me take up this example of a particular sort of a winding. Okay. So suppose you have a magnetic circuit like this. Okay, this is suppose the core. All right. All right. And suppose this is a winding. Okay. This is 1 dashed, all right? Then you have this winding. Okay, this is 2 dashed, and you have another winding like so. Okay, this is say 3 dashed, all right? So then you see, if you pass current through any of these coils, that will induce a flux to flow through this magnetic circuit here, right? This core. And that flux, by Faraday's law, will induce some voltages in the other two, right? And if you now know Lenz's law, you would know that the voltage induced in these two other coils will have a polarity such that they oppose the very cause which is responsible for their production. That is, suppose you pass a current in this direction, okay, through this. So you can easily see then that the direction of flux will be this, yeah. You can apply the corkscrew rule, and you can see that this is going to be the direction of the flux, all right. So if this flux is flowing here, then there must be a voltage induced in this fellow such that it should oppose the very cause. So it should send a flux in this direction, in the upward direction, right, to oppose this particular flux which is responsible for the production of an EMF here. All right. So what should be the direction of the current here then? Yeah, it's straightforward, isn't it? If it opposes, then it turns out that the current should come out from here. Okay. So then this is going to be a positive terminal, right? So for a positive terminal over here, a positive terminal here, note that this being a element such that there is a source here, right? So for a positive terminal here, a positive terminal is induced over here. All right. So we mark this by this circular dot. What about this other one? If this also has to oppose this flow of flux, then this must carry current in such a way that the resultant flux is in this direction, right? So it stands to reason then that the current should flow in this direction, all right, flowing out through this direction. So therefore, for a positive flux here, a positive polarity here, there should be a positive polarity here, all right. So this is how you mark out the polarities. Why this is useful will be clear to us in a moment. See, now we are taking all the trouble of looking at this magnetic coupling, yeah, coupling of this magnetic, yeah, the flux lines, yeah. So after a point, we don't want to have to do this. We want to just draw the circuit and be able to infer, yeah, and write down the voltage equations. So now similarly, we have seen the couplings between coils 1 and 2 and 1 and 3. What about between coils 2 and 3? Okay, you can check that if you pass a current through 3, the polarities will respect exactly the same thing. Maybe if you pass a current through this, you call this the positive terminal, then you'll see that, you know, the resultant flux will be in this direction. And in order to oppose that flux, this coil has to send a flux in this direction to the right. And in order to do that, yeah, in order to do that, the direction of the flux, the polarity. So suppose this current is sent in this direction, this being the source now, yeah. So if that is the direction of the current, then this will be the direction of the flux towards the bottom side, yeah, lower end. It flows in this direction, yeah, below. And in order to oppose that, this must then send a current in such a way that the flux due to this coil 1 should be to the right. And in order to send that, right, what should be the direction of the current flow? So you can check that even then the current must leave through this end. But if the current leaves through this end, this being now the source of the EMF, this becomes a positive terminal. So once again, you know, these circular dots check out, right? The triangles are representing the polarities of the mutual inductance between 1 and 2. The circular dots are representing the mutual inductance between 1 and 3. Now similarly, if you want to check between 2 and 3, you do the same thing, pass this current across any one of them. You know, these are relations are like symmetry. So once you have found the relation between 1 and 3, you don't need to again pass a current through 3 and see the polarity of 1, as I just argued. So similarly, you can now pass a current through 3 and check for the polarity of this. Okay, so take that as an exercise. And now, as an example of this problem, this kind of a circuit, we will take up the following. Okay. All right. Suppose this is the magnetic pole. All right. Looks pretty ugly. Excuse my bad drawing here. All right. Plus minus. And let's say you have a resistance here. Call it R1. All right. And pass a coil through this. Okay. All right, and then bring it out from here and close it with R2 over here. All right, that is one. The second coil we shall send here. All right, comes down. Oh, drawing. Okay. So the second coil, let's say it comes down over here, goes in this direction. Okay. All right. And it comes and closes the circuit over here. All right. And then there's a third coil which goes and attaches to the third limb. Yeah. So there are 3 coils here. This one has an inductance L1, this was has an inductance L2, and this was has an inductance L3. So far, so good. But now if you have to find out what the direction of the mutual couplings will be, then you'll have to again test. So here the dots are not given to you. So as the first exercise, you'll have to mark out the dots. Okay. So suppose this is the circular dot by which I want to denote the coupling between L1 and L2. So if this is a circular dot, for example, if you pass a current through it in this direction, forget about the source now. It is immaterial. Okay. In order, as we have shown in the previous figure, in order to mark out the dots, you don't need to assume any existence of a source. You can take any arbitrary polarity of the source and you can still mark out the dots. Okay. So suppose this, you mark out the dot for L1 and L2. So if this is the direction of current here, then this is going to be the flux. This is going to be the, and this is going to be the direction of flux. So if this fellow has to oppose this flux here, yeah, this fellow has to oppose this flux here, then it must send out a current in this direction, right? And in order to do that, therefore, this end must be the positive end, all right? Because now this becomes the source of the EMF. Remember, when you're assuming that this is being supplied with a current, this acts like a passive element. So therefore, the end through which the current enters becomes a positive terminal. But this is where the EMF is induced. So this then becomes a source, right? So for this, the end through which the current is leaving becomes a positive terminal. So therefore, positive terminal here and positive terminal here have been marked out. In the same fashion, you can also see that if this is the positive terminal, let's say I mark it out with a triangle here, the coupling with L1 and L3, right? Then in order to oppose this flux, this must send out a flux in this direction. And if it has to send out a flux in this direction, which way should the current travel? Yeah. So the current then should leave, as you might see, that the current should leave along this direction, right? So this becomes the positive terminal. Okay. So this is the positive terminal, this is the positive terminal. That's the coupling between L1 and L3. Now between L2 and L3, you can again try out either considering that there's a current through L2 and see the direction of induced EMF here, or you can do the other way around and you can check that without loss of generality. This is how you can mark. So the box is marking out the mutual inductance, the coupling between L2 and L3. The triangle marking out L1 and L3 and the dot marking out L1 and L2. All right. So now if you want to draw this circuit with these polarities marked, yeah, this is what the circuit will look like. R1. So this was the goal basically. I've just shown you how to mark out the polarities, but at the end of the day, once you have marked out the polarities, you want to forget about this magnetic circuit and we want to deal exclusively with the electrical circuit. So now you have these polarities marked here, right? And this R2. All right. This is V in. This is V in. Okay. Next, you have the second coil whose polarities have also been marked out. So this is going to be a box here and a dot circle here. Okay. And then you have the third coil. This is L2. This is L3. And we mark out the polarity of the third coil as well. So there's a box here and a triangle here. All right. Now we are in a position to write down the KVL. So consider this as I1, this as I2, this as I3. So I will straight away go to the Laplace domain and replace all these L's with S times L, and the R's will remain as they are. So the first equation, when I'm considering the first loop, is going to be as follows. V in is equal to, so again I can use the same technique as before without considering the mutual inductances, because those I have to consider separately. So what I'm going to do here is R1 plus R2 plus SL1 times I1 plus, okay, so the part of the loop that is shared between loop 1 and loop 2 is SL1, so there will be a minus sign, I'm sorry, as I just showed you a while back, this will be a minus sign. So minus times SL1 plus R2 into I2. So normally if you did not have this mutual induction, yeah, this would have sufficed. This would have basically covered all the terms that you require. So there are basically 1, 2, 3, 4, 5 terms, yeah. All right. But now you have to also consider the coupling factors between 1 and 2 and 1 and 3. So what are the currents that are actually causing this mutual induction? Yeah. So you see, for the coupling between 1 and 2, what is the current flowing through this circuit? It is basically I2 minus I3 according to this convention. But what will be the sign of this? That is what we are most interested in. Yeah. So let me write M12 and M13. Yeah. These are the two mutual induction terms that will be associated with this equation. But we don't yet know the sign. Let me write the currents that are flowing through this. Okay. So remember that the mutual induction here in L1 is due to the current that is flowing in L2. The mutual induction in L1 due to L3 is the current is owing to the current that is flowing through L3. So the current that is flowing through L3 is just I3, and this is going to be I2 minus I3. So all that I need to now bother about is the dot convention. That will tell me what the polarity of this will be, what the sign before M12 and M13 will be. So I'm going to first write the sign and then I'm going to explain, okay, how this works. So first I'm going to explain in a very sort of a shortcut manner so that you can remember it easily, and then I'm going to explain through the physics of this circuit. Okay, look at this here. Look at the way this circuit is driving the current. So once you have, again, remember, once you have drawn these dots, when you drew the dots, you did not consider any source here, right? That was independent of the source. But once you have drawn the dots, now you forget about the magnetic circuit. And if you just want to, by visual inspection, write down these equations, here is how to do it. So look at how the current is flowing in L1. I1 minus I2 is the current flowing through L1 according to your convention. And that has a direction downwards. So it is entering through the dot. Look at the current that is flowing through L2 according to your convention, that is I2 minus I3. This is the way you have written it algebraically. So I2 minus I3 is also a current that is flowing downwards. More importantly, it is a current that is entering the inductance through the dot. So the currents in both of these elements, I1 minus I2, of course if you had written it I2 minus I1, then the sign would have been different. But since you have written I1 minus I2, the current I1 minus I2 is flowing into the dot. So is the current I2 minus I3 flowing into the dot. Therefore, their mutual signs will be positive. What about I3? The current through L3. Look, the polarity here is the triangle and the polarity here is the triangle. So what is happening here? I1 minus I2 is entering through the dot, that is the triangle dot. On the other hand, I3 is leaving through the triangle dot. So their signs are opposing. Okay. So by following the same method, you should now be able to write out what the signs of the other two in the other two loops is. Of course, the rest of it is pretty trivial. But if you're writing this is the first equation, if you're writing the equation for the second loop, there will be what? There will be again M12, M21, M13, M23, right? So what will be the respective signs of these So if you're considering the current in this loop as I2 in this direction, the clockwise direction, and this I1, so the current through L1 is I2 minus I1, which is leaving through the dot. Okay. And what about this? I2 minus I3 is entering through the round dot. Yeah. So basically the coupling between M1 and M2, I mean L1 and L2, that is M12, should appear with a what sign? Should appear with a negative sign. So M12 should have a negative sign. All right. Because you're considering I2 minus I1. What about M21? Again, if you're considering it's basically straightforward. Again, if you're considering I2 minus I1, it's the same thing. All right. In general, M12 is considered to be equal to M21, but here, for the sake of generality, we are considering them to be denoted by two different symbols. Right. So again, if you're considering this, I2 minus I1 is entering through the circular dot. I2 minus I3 is entering through the circular dot, I'm sorry. And I2 minus I1 is leaving through the circular dot here. So M12 and M21 are both with a negative sign, provided you're multiplying this with, of course, there is an S, there has to be an S, okay? These are inductances themselves, so there has to be an S. Okay, so this is going to be I2 minus I3, and the product that goes with this is I2 minus I1. Yeah? All right. So we have here, yeah. So similarly, in the same fashion, if you now write for the third loop, you'll have to again consider the couplings of L3 with L2 and L1, and also L2 with L1 and L2. So complete this as an exercise. Okay, complete this as part of an exercise. But now, before we go into the next topic, just a short discussion on how this makes sense. So since I've written this first equation in its entirety, let us turn our attention to this about the mutual inductances here and why these signs make sense. Yeah. Now go back to the magnetic circuit. Remember when once we had got the dot convention, we had forgotten about the magnetic circuit. But now if you go back to the magnetic circuit, what does this mean? Yeah. So notice that what it basically means is, wait, am I getting this correctly? Yeah. Wait, this is yeah. M12 is basically the current through 2, no? L2. So it should be I2 minus I3, right? And M21 should be I2 minus I1. Yeah, excuse me, that was a mistake. Because the influence on this M1 on 2 is due to the current flowing through the inductor 2, which is basically I2 minus I3. And this is the influence of inductor 1 on inductor 2. So this is basically due to the current flowing through inductor 1. All right. So that is I2 minus I1. All right. I2 minus I1. Yes, that's correct. Yeah. So now look at the physics of this. How do we explain this situation here? That is the science of these. How do they even make sense? Now suppose you go back to the magnetic circuit, see how this current is behaving. This current is being driven in this direction. Consider the source now. Okay. So this is sending a flux in this direction. What about this? This same source, this voltage is sending a current in this direction. Yeah. So what is the direction of the flux here? The direction of the flux is downwards. All right. So it is basically coming here and adding to this. What about this? If you now look at this, the way this current is flowing here, the way this current is flowing here, the way this current is flowing here. So give the current directions according to the source now. So if this current is flowing through this, what is going to be this direction? The direction of the flux is actually this. So basically the flux produced by inductance 1 is supported by inductance 2 and opposed by inductance 3. Therefore you have a positive sign next to M12 and a negative sign next to M13. But remember, when we were writing these equations, we did not have to think of this. That is the whole utility of this dot convention. Once you have marked these out using the dot convention, then if you use the shortcut that I just mentioned, that is, just look at if the current that you have considered, if either both currents are entering through the dot or both are leaving through the dot, then it's a positive sign. But if one of them is entering through the dot in one loop and the other is leaving through the dot in the other loop, then it's the opposite sign. That's the shortcut. But if you go back to this, tracing this actual magnetic circuit, you will see that it works out because of this reason. But that is the beauty of this dot convention. Once you have marked it out using this dot convention, you no longer need to bother about what was going on in this original magnetic circuit. All right. So hopefully that clears that. The reason I wanted to discuss this is because in most of the books you will cover only up to this, when there is no mutual inductance, no coupling. All right, and that is pretty straightforward. By visual inspection, you can write this down as I just explained in the previous module. But when you have this, that's when you need to pay heed to the dot convention. Not just that, this is a weird sort of a coupling where by looking at this circuit alone, you would think that the first loop should not be influenced by current in the third loop. But because of this mutual induction, now the current in the third loop also influences the equation of the first loop. Okay, so that is an interesting bit. So having done that, now you're in a position to attempt the third exercise here. Don't worry, I'll have these put up shortly. So you should be able to solve this problem now. So here the circular dots are the coupling between L1 and L3. The square dots are the coupling between L3 and L2. And it is assumed that M12 is 0 and by extension M21 is also going to be 0. So let me just write that down so as to avoid confusion. M21 is equal to 0. So basically L1 and L2 are assumed to be uncoupled, decoupled. Okay, these two inductances don't have any coupling. Okay, all right. So we have covered mostly the KVL circuit analysis with passive elements. The next topic that we are going to take up now are op amps. So I'm not going to really cover how op amps are constructed and all. That's part of an electronics course that you should be undergoing. So they are built using differential amplifiers. Okay. So an op amp is built using differential amplifiers. Okay. That is how you construct an op amp. So why is it an active element? Okay. Because an op amp has a separate source of its own. Okay, an op amp cannot work unless it has a supply here. Okay, so this is a VCC. There's a supply here. I think it's plus 5 volts. I'm not mistaken. Okay, so there are supplies here to the two differential amplifiers. All right. So this is the symbolic representation of an op amp. This is a V out. So this is the inverting terminal. So an op amp has two terminals. One is the inverting terminal, one is the non-inverting terminal. And the difference between these two, so this is V plus and this is V minus and this is VD. So VD is basically V plus minus V minus. And the working principle of an op amp is that V out is equal to A times VD. Okay, this is the first equation, this is the second equation. And in addition, there are a few assumptions here. So it is assumed that an op amp has infinite input impedance and zero output impedance. So this will be clear shortly when I just draw the equivalent circuit of an op amp. Then you shall begin to see what, and this starts to make sense. All right. Okay. And additionally, so these are some of the assumptions of related with an op amp. All right. So additionally, you also consider that A tends to infinity. So this gain of this op-amp is very, very, very high. Obviously, you can imagine that these are ideal scenarios. Every op-amp that you will come across in life is a non-ideal op-amp. So this is going to be probably 50,000, 10 lakhs, some such large value, but obviously not infinity, right? It's not possible. Similarly, the input impedance is not going to be infinite. It's maybe going to be of some range of some kilo ohms, or maybe if you're lucky, some mega ohms, okay? But definitely not infinite. Similarly, this is never going to be zero. It might have some very small value, but the output impedance can never be exactly equal to zero. But for all practical purposes, compared with other circuits that you can imagine, built using passive elements, an op-amp outperforms any of them. Okay, the price to be paid is that this is an active element. It has to have a separate energy source, right? Okay, so this is the working principle of an op-amp. But first we will study the idealization of the op-amp. But using those ideal assumptions, how far can we get? Okay, so there are two types of inputs that can be applied to an op-amp. So first, let me consider an inverting input that is applied to an op-amp. Okay, so this is V out, and let's say this is Z1, and let's say this is V in. Okay, with this non-inverting terminal, then earthed. All right, and this is Z2, like so. All right. Now we want to derive the expression for the output is to input ratio. All right. So clearly here this is VD. So VD is here equal to 0 minus, let us solve this, V1. V1, right? That is the first equation, right? The next equation is V out is equal to A VD. Now here is where you make a simplifying assumption in the op-amp. It might seem a little counterintuitive and weird, but then you assume, so this is going to be equal to minus A V1, all right? And then you assume that if you want to get some meaningful, non-trivial sort of an output, then V1 is going to be minus V out by A, which then tends to 0. Okay. So therefore you assume that as if this is a virtual short. Okay. It is as if earthed here. Okay. That's the virtual short. Why virtual short? Because this V1 is, you are neglecting this, you are considering this to be 0. Right? Okay. Now, having gone through with this assumption, now you can apply KCL. So, what is KCL? The voltage at this terminal is V in. So, let's say V in minus, what is this V1? V1 is 0. Is it not? Because it is earthed. See, this VD itself tends to 0, and VD is nothing but minus of V1. So minus of V1 is 0, therefore V1 is 0, therefore this becomes basically like a, not just a virtual short, but it also becomes like a virtual ground under this assumption, right? So then you have V in minus 0 over Z1 is equal to V out minus V1, again that is 0. Right, upon Z2 with a minus sign. Why the minus sign? Because in one case you're considering the current coming in the other case you're considering the current going out. You could have of course done away with this equal to sign. You could have done away with this equal to sign and just said that I will sum up all the incoming currents, and that is going to be equal to 0. Why? Because again, remember that there is no current flowing in this direction. That is because of R in or Z in tending to infinity. So because there is infinite input impedance, no current flows into the op-amp. That is another assumption. So that is how you one by one, you piece by piece, you bring in the assumptions. So having gone through with these assumptions, you can see that for an ideal op-amp, in this configuration, that is in the inverting terminal configuration, it leads to V out by V in is equal to minus Z2 over Z1. All right? But Z1 and Z2 are the impedances. Along similar lines, if you now consider a non-inverting mode operation for the ideal op-amp. All right? So for the ideal op-amp, non-inverting mode operation, you have something like this. Let's say you apply an input voltage here. Okay, this is V in. This is Z2. It is basically divided here. And then you have this loop. And then I think this is Z1. Right? So this is the mode. Once again, as before, you can assume that V out is equal to nothing but A times VD. Yeah. So what is VD now? This is A times V in minus, let's call this V1. V1. Okay, this is step 1. And what is V1? Just look at V1. V1, this is a voltage divider, no? So therefore, V out divided by Z1 plus Z2, that is the current flowing through this. Why? Because there is no current flowing in this direction. This is 0. Sorry, this is 0 current, no? This IA is equal to 0. Again, due to infinite input impedance, there is no current flowing in this. So whatever is flowing through this circuit is also flowing through this circuit. So the current is basically flowing continually through this circuit. So basically the entire current V out, and it goes to the ground. So basically this is the current. And what fraction of it is appearing across this terminal? Z1 times, right? So this is basically nothing but V1. So now if you apply this, same principle again. So you apply this V in minus V1 is equal to V out over A, which tends to 0, right? If this tends to 0, then V in is basically equal to V1, right? Having come across this, then what is V out? V out is nothing but given by Z1 plus Z2 upon Z1 into V1 is equal to Z1 plus Z2 upon Z1 into V in, which then implies that V out over V in, the transfer function is going to be Z1 plus Z2 upon Z1, or 1 plus Z2 upon Z1. So this is the transfer function of an ideal op-amp over a non-inverting input. Okay, when the operation is over a non-inverting input. Now I will show you the now I will show you the equivalent circuit of an op-amp, a non-ideal op-amp. Okay, and then you will see that by bringing in those assumptions one by one, how that whole thing falls into place. Okay, so if this is an op-amp, this is an op-amp whose equivalent circuit I'm now drawing. So suppose this is V out. Okay, small V out. then this is going to be the output resistance. It can be an impedance in general, but here we are considering a resistance. All right. I'm denoting a dependent voltage source by the diamond sign, this round one, circular one. This is a VD. All right. Yeah. This is earth. This is grounded. All right. Okay. And this is going to be the non-inverting input. This is plus. And then instead of the open circuit, you now have a input resistance or impedance, as the case may be. Again, you can choose this to be an impedance. I'm choosing it to be a resistance for the time being. Okay. All right. Yeah. So there you go. This is basically VD, which is VD. This is nothing but, let's call this V plus, and this is V minus. So then VD is nothing but V plus minus V minus. All right. So that is going to be the equivalent circuit of an op-amp, of a non-ideal op-amp. All right. Now in this, things become simpler in the sense that you don't have to make all those assumptions. You don't have to assume A is infinite, R in is infinite, or R0 is R0, that is the output impedance is 0. Yeah, you can just write the KCL simply by following standard methods. And if you are good at solving using KCL, then after you've obtained everything, all the transfer function and all, according to whatever assumptions are given, one by one you can plug in those assumptions. So for example, here, whatever I have drawn within this dash line, this dash box is internal to the op-amp. Now let's say I'm connecting, this is an example, okay? So I'm connecting a circuit like so. So the inverting end is grounded through a resistance R, and the non-inverting input end is given a voltage V in, all right? In addition, this is shorted like so. So any connection that is outside this dash box is basically external to the op-amp. Excuse me. All right. So now we want to write the KCL, right? Okay. So first, before that, notice that V out is shorted with V minus. So basically, V out is equal to V minus. That is equation 1. Second equation is V in is equal to V plus. That is equation 2. Now we are trying to write the KCL in this node, suppose. All right. So let's say the current leaving this node is V minus by R. And the current entering this node is what? Okay, let's see which direction eventually comes out to. So the current entering this node through this direction, let's say, is V minus minus V plus over R in. All right? Yeah. Oh, no, sorry. This should be the current leaving, no? Yeah. Yeah. Now it's fine because it's supposed to flow in this direction. So V plus should be at a higher potential. Yeah. V plus minus V minus. That is the current entering. Okay, no, forget it. This is messing things up. Let me write it in neat conventional fashion. Yeah. So basically, let's assume certain directions of these currents. So let's say this is the direction of the current here. So the incoming current to this node is basically flowing from V plus to V minus, V plus minus V minus over R in. Okay, that's the current flowing, and the current flowing out of here is V minus minus 0. So I'm not writing that, by R. All right. What is the other current? That is this current. So what is the direction of this current? Suppose I assume this direction to be, suppose V out is higher. So then this current is nothing but V out minus A, what is VD? VD is nothing but, yeah, I've already written that. Anyway, this is a repetition. V plus minus V minus, yeah, divided by R naught. So the direction I'm assuming is this, yeah, so this is the direction of the current. So that is also a current that is leaving this circuit, right? So let me write this as V out minus A, V plus minus V minus over R naught. Now what I'm going to do is, I know that V out is equal to V minus and V in is equal to V plus. So I'm just going to put everything in terms of V in and V out. That will help me in obtaining the so-called transfer function, right? Of course, this is a transfer function, but of course it does not involve any term related to S because I've only considered purely resistive loops here. I could have in general considered this to be Z, and you know, as I said, this to be Z in and this to be Z out. Wouldn't have mattered much because once we've seen that, we can use it this way. All right, so should I write it in this page? Okay, so V plus is basically V in, yeah, and V out. Okay, so V out related terms can be all pushed to the other side. Let me check carefully and before I go to the next slide. Okay, so basically, yeah. So I've actually copied it in a piece of paper so that I can write it quickly. So you check, I think this is right. 1 by R plus 1 by R naught plus A by R naught plus 1 by R in. This is equal to V in over 1 by R in plus A by R naught, right? So therefore, now if you want to find out V O by V in, this is going to be the ratio 1 by R in plus A by R naught upon 1 by R plus 1 by R naught plus A by R naught plus 1 by R in. All right. So now gradually you take these three cases separately, okay, and then combine them together and see. So first you consider A tending to infinity only, R0 and R in are not assumed to be ideal. Then you consider R naught tending to 0, the rest two parameters not being non-ideal. Then you consider R in tending to infinity and A and R naught being non-ideal, okay, and see if you can get this close to unity. So the goal of this particular circuit, I didn't tell you initially, the goal of this particular circuit that was designed using this op-amp was to get a unity gain, okay. So can you get this close to unity? Okay, so take this as an exercise. So this was the goal, okay, and tell me, you have to tell me which one of these strategies, like if this one alone is holding and the other two do not hold, can you get close to this? If this one alone holds and the other two do not hold, can you get close to this? And similarly, if this one alone holds and the other two do not hold, can you get close to this? And which one meeting, if you have to give, if you're given the choice that you have to meet, you can meet at most one of these idealizations, the other two cannot. Which one should you go for? So that is like a designer's choice, okay? Given that you cannot have more than one idealization, the other two have to be non-ideal. Which one, when chosen to be ideal, gives you the closest to this, okay? So that is the problem, and having solved this, the final problem or the final exercise is this. So don't worry, I will share these slides, so you don't have to copy in a hurry right now. These will be there with you when you'll be trying to solve these problems, okay? So hope you enjoyed these solving these exercises, and also hope you're enjoying the lectures. So thank you very much. With that, we've come to the end of lecture 2.